Okay, so last video we were discussing the idea of basis vectors. And I got just one more quick thing to say about that section, but then where we're going to go is we're going to move into the topic of dimension, right? So now I understand that it's fairly easy and intuitive for us to think about the dimension of, say, a two-dimensional plane, where maybe you have a length and a width, or dimensions of space, you have a length, a width, height. So I know that although this can be, it seems like this concept would be extremely intuitive and not worth devoting a section to, but to mathematicians, they when we're discussing dimension, we want to make sure our language is as exact as possible, so that we can communicate the ideas. Now, so the last bit of information I wanted to state about the basis, and again, if it's, let's say it's been a couple days since you watched the video on basis, just remember that that in a plane, or say, let's just take the XY plane, plotting points, so over 2, up 3, can be thought of as basically the weights, the scalars attached to some basis vectors in a linear combination. And the ideas that we learned last video were basically that although the majority of the time we use the standard basis of 1, 0, 0, 1 for our vectors, that any two vectors, as long as they meet the qualifications that we discussed, that any two vectors can serve as a basis. And what comes out of that is, yes, the graphing paper that you are about to graph may look a lot different than what you're used to, but you can still reach all of the same points in your vector space that you could in the normal graphing paper. So what's this last idea? So let's recap really quickly. So in this case, x is going to represent the vector in the standard basis. So if I said plot the point 8, 7, you would go to the right 8, up 7. That's what I'm talking about right now. So that's just the normal points, the normal vectors in the standard basis. Now, when you see, once you have a different basis, that and you still want to be able to plot the same points, right? You have to impose a coordinate system, and then you plot within your new coordinate system. But this notation here is telling you that the coordinate vector, so it's the same location, okay? But it is the coordinate vector in the new basis. Now, you can kind of look up here at the picture where you start off with x, okay? So let's just say some vector in your vector space. And you can see how a transformation takes place where we are moving from vector x to the coordinate vector of x. So new basis from standard basis. And all this is trying to point out is this, just like any function can map from one from one location to another. This is just a special type of mapping, what we call a one-to-one, or in other words, a linear transformation. It's a linear mapping. From what? Well, from V, which is the normal vector space, to Rn. And what do they mean by Rn? Well, of course, if you think about your vectors are always in, when we're looking at these column vectors, they're always n by 1 vectors. Okay, so with that behind us, let's now discuss a little bit about, let's discuss the topic of dimension a little bit. And more importantly, let's actually see if we can define what we mean when we say dimension. Okay, so what I have written here, I'll get to the theorem in just a second, but just remember that all vectors can be written as these column vectors, where you can think of it, of course, it's one column and n rows, right? Now, a basis obviously is a set of vectors where you would have a v1, a v2, depending on what the basis is what it's a basis for. That behind us, let me actually see if I can read the theorem, and then we'll try some in other words just to make sure that we're walking away with the right information. So theorem 9 reads as follows. So it says, it's an if a vector space V has a basis, right? So here we go. So if it does have a basis, then any set in V containing more than n vectors must be linearly dependent. Now hold on for a second. Wait a minute. So let's start with, let's try to put some things together here. So let's stick with R2 for a second. Right? So if we are in R2, we're in two-dimensional space. How many vectors should be in that basis? Exactly. There should be 2 vectors in that basis. So when they say, look, if any set is containing more than n vectors, so in this case, n would be 2 because this is R2. So if we had more vectors than just 2, then the vectors must be linearly dependent. You could think of it as, once I throw a third vector in there, then I'm going to have free variables. If I have free variables, then I can actually take my homogeneous equation, I would have solutions to that equation that are other than just the trivial solution, other than just choosing scalar weights of 0. That's the idea, okay? Okay, so let's take a look at Theorem 10. Theorem 10 states, if a vector space has a basis of n vectors. Okay, now, the previous theorem was discussing more than n vectors. So if we have a vector space V that has a basis of exactly n vectors, then every basis of V must consist exactly of n vectors. In other words, yes, there are a whole lot of bases for R2. That's why you could have a whole lot of different graphing paper that you could use when plotting points. But the thing that they would all have in common is they would all have 2 vectors. Now, when you count up how many, so obviously a basis is a set, right? And so just some language here. When you discuss how many elements are in a set, like for example, the set that I've written here has 2 elements, we would say that the cardinality, okay, that's the cardinality of the set is 2. So in this case, you can kind of get the gist that what they're saying is, look, you might have many different basis vectors for an R2 vector space, but all of them will have exactly 2 vectors as the cardinality, okay? All right, well then, how do we get from here to dimension? So let me read, and then I'll see if I can give you in other words. So now we say if V, so the vector space V, is spanned by, now a finite set, meaning meaning that the number of elements in the set is finite, it's not infinite. So this had 2 elements, so that's a finite set. So if vector space V is spanned by a finite set, then V is said to be finite dimensional. And here it is. And the dimension of V, denoted dim V, what is the dimension? It is the number of vectors in the basis. So if I tell you that if I give you a basis and I say this is the basis for some vector space, let me just throw some things out here. Ready? Now, I don't give you any more information. Let's just say all I give you is this set of vectors. But then I tell you, hey, but for sure, this set is a basis. And then you say a basis for what vector space? And I say, I'm not going to tell you. I'm not going to tell you what vector space it is, but I'm telling you it is a basis. Well, you don't have to continue to ask me questions about it, because all you really need to know is how many vectors are in this set. And that'll automatically tell you what dimension that we're dealing with. So I have 3 vectors in this basis, so therefore I must be in R3. Okay, so I'm going to highlight that how we denote the dimension of a vector space, and that way you just have that highlighted. Now let me talk a little bit about some other cases. So the dimension of the 0 vector is defined to be 0. That's an important point, is defined to be 0. But we won't stay there very long. But so if you have the 0 vector and that's all you have, we have defined the dimension of the 0 vector to be 0. If your vector space is not spanned by a finite set, right? In other words, you have an infinite amount of vectors in your basis, you could think of it. Then we say that V is infinite dimensional. So what I care about, what you care about right now, is finite dimensional dimensions. And let's just go ahead and take a look at what we have here. So what I've produced for you, so A, B, C. These are 3 very different looking vectors in R2, right? So you can look at the sets of vectors. These are very different looking vectors. And what I want to tell you is each of these is a basis for R2. Because why? Why can I say each of them, each is a basis? For R2. Notice what I just said. I said each A, B, C. Each of these are a basis for R2. Now, can I say that, well, it's a basis for R2 because there's 2 vectors? Absolutely not. You can't, just because your set has 2 vectors doesn't mean it's a basis. But if it's a basis, then it must, if it's a basis of R2, then it must have 2 vectors in the set. I'll say that again, right? It's the switching of the if-then statement. It's just because you have 2 vectors in a set does not mean that those 2 vectors are a basis for R2. But if you have a basis for R2, then you are guaranteed that you will have 2 vectors in your set. That's what I was trying to get across. Now, why do I get to make the statement that they are both, or all 3 of these, A, B, and C, all are bases, different bases for R2? It's because they meet the qualifications that each of them span all of R2. That means I can use those points to plot any other points that I want in R2. And then second, each is linearly independent, right? Meaning they're not multiples of each other. Okay. Let's go ahead and continue here. So let's actually try a question. So the example reads as follows. It says, let or assume that H is equal to the span of the following two vectors, v1, v2. And I actually have defined v1 and v2 for you. Our job, your job, is to find a basis and the dimension of H. So I need to know a little bit more information about H. Come back to me. Ready? Come back to me. Only thing I know about H right now is here's a point in H and here's a point in H. That's all I know. What I want to do is I want a basis and I want to know the dimension. Let's start with the basis. Well, let's take a look at our vectors that were given. So this is, remember, all vectors, this is an n by 1, this is an n by 1. Let's go ahead and fill in here. So this is 3 rows, 1 column, so this is a 3 by 1. This is a 3 by 1. So let's you and I agree that this vector and this vector is in R3. Okay? Now, the question, the question that we have to assume here is, and I'm going to show you the geometry of what's really happening here. The question is, or not, are these two vectors linearly independent or dependent? So if these are my basis vectors, right? So if the statement, and I don't know if I made that clear when I was reading it, if the basis for H is V1 and V2, what I should have been a little bit more clear for is find a basis, meaning find if V1 and V2 are a basis, is a better way of wording that. Are a basis for, you could word as for R3 or R2 or whatnot. So let me rewrite it. So find the dimension of H and well, we'll just assume that we won't go through and write that question again. So yeah, so this is, let me just make the statement that V1 and V2 is the basis of H. So, okay. But is it the basis? So if it's a basis for what, though? You have to think about it for, is this for R3 or a basis for R2? Well, let's start with the fact that to have a basis for R3, we would need 3 vectors, right? So we only have 2 vectors. So what you can think about is, yes, it is true, each vector is in 3-dimensional space, right? Each vector has a length, width, height, if you will. But the idea is, because I only have 2 of the vectors, then at best that I can simply span, the span of the two vectors would just be what? It would be a plane. So you can imagine a plane in space, and that those points that are on that plane represent this the space. So I would need another vector in order to span all of R3, so I can only span R2. So what is the dimension? What is the dimension of H? Well, here's what you should do. Go to the basis, right, if you're given a basis, and count how many vectors are in your basis. So I'm counting right now. I have one vector here, one vector here. I only have two vectors in my basis. Therefore, the dimension of H is 2. Okay. So let's try another one here. So this one is read as find the dimension of the following subspace. Okay, so H is defined as follows. And we're told that A, B, C, D, these are all real numbers, okay, in the real number system. Now, here's what I'd like to be able to do to answer this question. I would like to have a basis. And then I would like to be able to count how many vectors are in the basis. Because as soon as I do that, I can answer the question of what the dimension of H is. I just need a basis first. So let's start with how do I actually set up a basis? Well, let's think about the fact that looking inside of H here, we have how many different variables that we're dealing with. So, well, we have A, B, C, D. So we can think about A, B, C, D. Each of these are going to represent its own vector. So let me see if I can start writing out. So let's start with the A. Let's actually write out. So I'm actually going to, if I have variables A, B, C, D, I have four variables. That means I'm going to have 4 different vectors. Now, are all 4 vectors part of the basis? We will know very soon. Ready? Let's start with just the A vector. Okay, so let's see if you can follow me here. So looking at row 1, how many times does A show up? Row 1, just one time, right? So I'm going to put a 1 here. All right, let's look at row 2. How many times does A show up? 5. Row 3, 0. Row 4, how many times does A show up? 0. Okay, let's go to B. So how many times does B show up in row 1? -3. In row 2, 0 times. In row 3, 1 time. In row 4, 0 times. All right, what about V sub 3? So looking at C, it shows up 6 times in the first row, 0 times in the second row, -2 times in the third row, and 0 times in the fourth row. And now let's look at D. So D shows up 0 times in row 1, 4 times row 2, -1, and 5. Now, so hold on for 1 second, because although I'm leaning towards saying that the dimension of H is 4, right? Fourth dimensional, but we don't really know that yet, because we got to make sure that each of these bases are linearly independent. So how do I do that? Well, all that is required is we're going to take each of those vectors and set them up as columns in a matrix. Ready? So we're going to put the V1, V2, V3, V4, and each is going to serve as its own column. Ready? So 1, 5, 0, 0, negative 3, 0, 1, 0, 6, 0, negative 2, 0, 0, 4, negative 1, 5. Okay. Now, notice this next step. I am going to row reduce, but I'm not actually going to set it equal to something. I'm going to row reduce this matrix, and I want to look to see how many pivot columns there are, or in other words, how many basic variables versus free variables. All right, so let's say we row reduce this matrix. We would get 1, 0, 0, 0, 0, 1, 0, 0, 0, negative 2, 0, 0, and 0, 0, 1, 0. Okay. Now, our job right now is to look in here and pick out how many pivot columns with pivot positions we have. So let's agree, so here's a pivot. So column 1, V1 is good. Here's a pivot. So V sub 2 is part of the basis. Now, do you see that this third column does not have a pivot position? That's not a pivot column. That's a free variable. Now, if you have free variables, you have ways of getting to 0 aside from just the trivial solution, correct? So this entire V sub 3 column has got to go. Now, the fourth column, that also has a pivot position, so that's going to stay. So, in other words, V sub 1 is part of the basis, as is V sub 2, as is V sub 4. V sub 3, you can just see that it's not a pivot column. It is a free variable. So if you want to maintain linear independence, then you're going to have to throw that out. Okay? So now we have our basis for H. But let's answer the question. What is the dimension of H? So dimension of H equals, ready, just count. All you got to do is count how many vectors are in the basis. 1, 2, 3. There you go. So we have 3, or a dimension of 3. All right. So at the bottom of the screen here, we're taking a look at some different subspaces of R3, right? So this is three-dimensional space, as is this, as is this. Notice that in the very first picture, this is a subspace of R3, which is just a line, right, running through the origin. And we would say that is one-dimensional. That's a one-dimensional subspace of R3. It's also true that you could have a plane, right? Any subspace spanned by two vectors, two linearly independent vectors would be a plane. And again, notice the plane is moving through the origin. Right? If it's not moving through the origin, if you don't have the zero vector, you don't have a vector space, or a subspace, since a subspace is just a vector space. And then obviously in that third picture, this is R3 itself. So this would be another, since every vector space is a subspace and every subspace is a vector space, then you can see where I'm going with these three different pictures. Okay, So to make Theorem 11 and Theorem 12 come alive, I'm gonna punt on both of these for just a second and I'll come back to them during an example. I'm going to quickly read this, find the dimension of a null space and a column space, but again, on the next page, I'm going to do an example that'll help you solidify this point. Okay, so the dimension of a null space is the number of free variables, right, in the equation ax equals 0. And the dimension of the column space is the number of pivot columns. Now, listen, you either have a basic variable or a free variable. You either have a pivot column or a non-pivot column. Now, one of those is contributing to the dimension of the null space. The other is contributing to the dimension of the column space. So take, for example, example 5. So the question just says, find the dimensions of the null space and the column space. How do you want to tackle this? Well, the first thing you want to do is, let's reduce this, right? Now, we want to row reduce by setting A equal to 0. Are you ready? So what I'm going to do right now is I'm going to go ahead and show you what would happen if if you have A written here, and then you turn it into an augmented matrix by putting that last column of all zeros. And now what's about to pop up is what it would look like if you row reduce. Okay, so this is what it would look like. So I have 1, 0, 0, negative 2, 0, 0, 2, 1, 0, 3, 2, 0, negative 1, negative 2, 0, and 0, 0, 0. Okay. So notice what is written at the very top. It says the dimension of the null space is the number of free variables. Okay. And the dimension of the column space is the number of pivot columns. All right. So you and I go down the line. So let me erase that. Let's go down the line here. So the first column, that is a pivot column, right? So that should contribute to the column space. So I'll put a tally mark of 1 over here for the column space. All right, the next column, that's not a pivot column, that's a free variable. So that second column is going to contribute to the dimension of the null space. All right, let's take a look at the rest of them here. So we also have the third column. Now I did not RREF. This is just row reduced. It's not. We could. At least I don't think. It's hard for me to remember if I just copied this, or I actually did row reduce it or row echelon. Go through the RREF versus an REF. But the idea is this third column would also be a pivot column, right? So let's see here. So we have, so let me make sure I read that correctly. The dimension of a null space is the number of free variables in the equation. The dimension of the column space is the number of pivot columns in A. Yeah, so we should have 3 pivot columns, and we should have, 2 pivot columns, which is what I've circled here and here. And then the rest are going to act as free variables. So sometimes I get distracted and second guess if I just said something incorrectly. Okay, so the pivot columns, there's only 2 pivot columns in this matrix, so the dimension of the column space is 2. There's 3 non-pivot columns, there's 3 free variables, so therefore the dimension of the null space is 3. Does that make sense? Does that make sense? I didn't hear you. You gotta talk to me through the internet. All right, and finally, let's answer. Almost done with this section, so just stay with me. So the dimension, let's just say, so let's go ahead and take a look at the theorems that we skipped over here. Ready? Okay, so the last bit of material that we want to cover, and I was going to try to chop this up into 2 different videos, but I think we're just going to, because we're almost done, I'm just going to press through and finish it. So, takeaway, pivot columns contribute to column space. Free variables contribute to null space. And now what we want to do is look at some of our theorems on rank. But actually, you know what? I will take this information and bring it to the next video. So all we're going to do is just going to look at the rank of a matrix and the dimension of the null space of a matrix. And that, I do think we'll call it quits, and I'll see you soon.